Folks, I had a request to also kind of take a look at the questions that I took up during class today because the sound was a little bit choppy on the Google Meet for some people. So I'm just going to kind of run through these. If you saw these ones okay, you can just fast forward to the other two questions that were posted new at the end. So in this proof, we talked about a couple of things that were really important to note. If you have the cross product of two collinear vectors, so they could be actually equal, like this A cross A or B cross B, or they could just be any scalar multiple of each other, that cross product will always be 0. And we talked about a few different reasonings for that. Probably the easiest to see is this definition in terms of magnitude, sine, theta. We know that if the vectors are collinear, the sine of the angle between them, theta, is 0, and sine 0 is 0. Other ways of thinking about that messy diagram down there, is the idea that if these two vectors formed a parallelogram, they're actually parallel lines. So the kind of two sides of a parallelogram, if they're actually parallel, there's no area to that shape. So when we do the distributive property here, it is really important to keep the order correct and to remember that the cross product is not commutative. So we get A cross A and A cross B here from the red arrows. Then we get minus B cross A, remembering that we can't just, like we do when we're foiling an algebraic expression with real numbers, we can't do that with cross product and vectors. These two are not the same thing. And then we get minus B cross B. But knowing that scalar multiple or collinear or equal vectors would be 0, we get a 0 there, a 0 there, and we know that then minus B cross A is the negative of A cross B. So then that double negative would make a positive, so we'd have two A cross B's, which is our right-hand side. With this one, we're just going to use the identity that the cross product, the magnitude of the cross product, is the area of that parallelogram that would be formed. Now, we're just using vectors P and Q, including that variable of A, to find the value of P cross Q, which is going to have components. The last two components will have an A value in there, but then the magnitude of that cross product would equal the 35. So here we've squared both sides and then FOIL out these two terms and get this big messy thing, collect like terms, bring the 35 over, and it factors. You could just use the quadratic formula if it didn't factor though. Important thing to remember here, a couple kind of big ideas, is that if we're looking for the area of a triangle, that's half the area of the related parallelogram. So if we had a parallelogram, kind of draw this out over here, if we had, say, that parallelogram, then the triangle that would be formed between 3 of those points is half the area. So the magnitude of the cross product there is the area of the whole parallelogram, but we're just doing the area of the triangle, which is half of that. So we have that divided by 2. The other important thing is that we're dealing with points. These are not vectors. They are just points in space. We need to figure out what vector AB and AC would be to be able to do the cross product of those. So then once we do the cross product of AB cross AC, we get negative 3, 11, 10, and then doing the magnitude of that, we can figure out the area. Here is one of the tension questions. So we've got an object with a mass of 10 kilograms. So remember the force of gravity is the mass times 9.8. So that's going to be 98 newtons. Suspended by two pieces of rope that make an angles of 30 degrees and 40 degrees with the horizontal. So here I've got this object. The force down is 98, and it's got a 30-degree angle and a 45-degree angle with the horizontal, and we want to figure out the tension in each of the two pieces of rope. So we would know that there's going to be a tension here, T1 plus T2 would equal the equilibrium force that is working against and equal to the force of gravity. So I'm just going to call that the resultant or equilibrium force. So here, I know that I could redraw T2 up here, head to tail there. And then the important thing here is to be able to figure out what would be happening in the angles. So I think that one of the easiest ways to see this is to look at this triangle here on that triangle on the right and see that if this angle's 45, I know that that's a 90, so this angle here would be 45 in there. And then the opposite one, looking at the triangle out there, looking at my triangle on the left side, I've got a 30-degree angle there, so that must be a 60-degree angle at the bottom. I can then use a couple different ways I could look at this. I know that this angle here then is 105, and that would be the C pattern there with parallel lines, so that angle in here is 180 minus 105, which is 75 degrees. So if I were to redraw this, I'd have T1, T2, and the resultant, and I would know that this is 60 degrees, this is 75 degrees, and then subtracting from 180 minus 60 minus 75 is 45 degrees up there. Another way of seeing that top one is that would be a Z pattern like that to get a 45-degree angle up there. So we can now figure out the magnitude of the tension using the sine law, because I know the magnitude here is 98. So the magnitude of T1 over sine 45 is 98 over sine 75. So the magnitude of T1 I get as 71.74 newtons. And then similarly for T2, the magnitude of T2 over sine 60
Mr. Meyer, you have a call at 701.
equals 98 over sine 75. So then the magnitude of T2 would be 87.86 newtons. So therefore the tensions in the rope are 71.74 newtons and 87.86 newtons. And this is one of the few cases where you don't actually have to list a direction per se, because you would have it has to be in the direction of the rope. So that's just kind of a given. Okay, we've got a current one. Kayla wishes to swim from one side of the river, which has a current speed of 2 kilometers per hour, to the other side directly across from her starting point. She can swim a speed of 3 kilometers per hour in still water. So she wants to go straight across from where she started. So remember that we would have, she wants her resultant to be straight across. And remember that we always say, like, the plane plus the wind equals the resultant. And that's the same as like the boat plus the current equals the resultant, or the swimming plus the current equals the resultant. So that's kind of what we have. We know the answer. We know the resultant wants to be straight across. Now, she would have to swim this way. She has to go like upstream. That's her swimming velocity. And then the current would be going that way. So A says, what angle should she swim if she wishes to swim directly across? So if I put that theta, I would say that I'm going to use sine because I know the opposite and the hypotenuse. So sine theta is, the current is 2 and the and her swimming speed is 3. So theta would be about 41.81 degrees, but it actually says what angle to the bank. So that means that you're actually looking for this angle in there. So we have to subtract that from 90 degrees. So it would be 48.19 degrees from the bank. Now, if the river has a width of 300 meters, how long will it take her to cross? I'm just going to erase this because we don't need that. So for B, we're going to have to find out the magnitude of the resultant. So the magnitude of the resultant is the square root of 3 squared minus 2 squared. Because we have that nice right angle, it's not actually going to be trig at all, just Pythagorean theorem. So it's about 2.24 kilometers per hour. Now, this is saying if it's 300 meters, how long will it take her to cross? We know that distance is speed times time. So time is the distance over the speed. So that's 0.3 divided by, 2.24. Make sure you've got the right units because that was in meters and we've got kilometers per hour.
Ms. Reinhardt, call 5601. Ms. Reinhardt.
So 0.3 divided by 2.24 is 0.1339 hours. But I would just multiply that by 60 and say that it was 8 minutes. So it'll take her 8 minutes to swim across the river. And then for C, if her speed and the river speed had been reversed, why would it not be possible? So what if we tried to kind of like redraw this? And again, say like, I want to find my resultant going straight across, and she's going to swim this way, and the current is going to bring her down this way. And what if I said the magnitude of the current is 3 and the magnitude of her swimming speed is 2? Now that doesn't work because her swimming speed has to be the hypotenuse. So if she tries to head straight across, regardless of what's going to happen, it would not work because the biggest speed has to be the hypotenuse. So her swimming speed in still water would have to be the hypotenuse in order for us to get straight across the bank. So the swimming speed has to be greater than the current speed, or else that won't work.